Welcome to Global Byte. Please subscribe and hit the bell icon for more breaking updates. In labs and factories worldwide, a silent race is underway for technological supremacy. Measured in nanometers, the ability to manufacture 2-nanometer chips is the pinnacle of human engineering, powering AI, supercomputing, and next-gen devices. For decades, Taiwan's TSMC has led this domain, but now China signals its intent to join, raising questions about a potential shift in global power. This race isn't just technical, it's about geopolitics, economics, and the future of innovation. As we explore this contest, we'll separate fact from hype and reveal why the outcome matters to everyone, everywhere. The journey to today's cutting-edge 2-nanometer chips began with a single, world-changing invention, the transistor. In the late 1940s, a handful of visionary scientists at Bell Labs created a tiny device that could switch and amplify electrical signals, laying the foundation for the digital age. This breakthrough would soon transform the world of electronics forever. Before transistors, electronics relied on bulky, fragile vacuum tubes that consumed enormous amounts of power and generated intense heat. The transistor's arrival made it possible to shrink devices dramatically, making electronics more reliable, efficient, and portable. Radios, hearing aids, and computers all became smaller and more accessible. The next leap came in the 1950s, with the invention of the integrated circuit. By combining multiple transistors and components onto a single chip, engineers sparked the microchip revolution. This innovation powered everything from pocket calculators to the first supercomputers and set the stage for the information age. In 1965, Intel co-founder Gordon Moore famously predicted that the number of transistors on a chip would double every 2 years, a prophecy known as Moore's Law. This vision became a guiding principle, fueling relentless innovation to make chips ever smaller, faster, and more affordable, decade after decade. Central to this progress was lithography, the process of etching intricate circuits onto silicon wafers. Over time, lithography evolved from using visible light to deep ultraviolet, and now to extreme ultraviolet, EUV technology, as engineers pushed the limits of miniaturization. EUV lithography, developed over decades and requiring billions in investment, uses ultra-short wavelengths of light to carve out features just a few nanometers wide. This allows for the creation of transistors so small, they're invisible to the naked eye, enabling today's most advanced chips. At the heart of this technology is Dutch company ASML, the world's only supplier of EUV lithography machines. Each machine is a marvel of engineering, assembled from hundreds of thousands of parts, and shipped to only a handful of the world's leading chip makers. Access to EUV technology has become the dividing line in advanced chip making, shaping the global semiconductor landscape and influencing everything from international trade to the future of computing. 2 nanometers is unimaginably small. A human hair is 80,000 nanometers wide. Chips at this scale use nanosheet, or gate-all-around transistors for greater speed and efficiency. This leap enables faster, more power-efficient devices, from AI data centers to smartphones and autonomous vehicles. Mastering 2-nanometer technology is a monumental engineering and financial challenge, reserved for the world's most advanced companies. The practical impact is vast: smarter devices, longer battery life, and breakthroughs in AI and scientific research. The 2-nanometer node is more than a technical milestone, it's a strategic asset. Whoever leads here sets the pace for global innovation. That's why the race is so intense, with national security and economic leadership at stake. TSMC, based in Taiwan, is the only company mass-producing 2-nanometer chips as of late 2025. Its Kaohsiung Fab 22 facility represents the cutting edge of semiconductor manufacturing. Tech giants like Apple and Nvidia invest billions to secure TSMC's technology, reinforcing Taiwan's central role in the global tech ecosystem. This dominance is Taiwan's silicon shield, a deterrent against conflict as the world relies on its chips. Despite global expansion, TSMC keeps its most advanced processes in Taiwan, maintaining its strategic indispensability. The world's dependence on TSMC for next-gen chips is both a strength and a risk, fueling urgent efforts elsewhere to build domestic capacity. In late 2025, Huawei's patent for making 2-nanometer chips using older DUV lithography sent shockwaves through the industry. With China blocked from EUV machines by US-led export controls, this patent hinted at a possible workaround. If viable, it could let China bypass sanctions and achieve advanced chip-making independence. However, experts caution that moving from patent to mass production is a massive leap. Dove methods likely yield too few usable chips to be practical. As of early 2026, there's no evidence of successful mass production in China at this scale. The patent symbolizes China's ambition and ingenuity, but remains unproven. Still, China is rapidly advancing in other chip sectors, determined to close the technology gap. China's most formidable obstacle in the race to produce cutting-edge 2-nanometer chips is its lack of access to extreme ultraviolet, or EUV, lithography technology. This technology is absolutely essential for manufacturing the world's most advanced semiconductors, and it is monopolized by the Dutch company ASML. The United States, working closely with the Netherlands and other allies, has imposed strict export controls that prevent ASML from selling its EUV machines to China. These controls are part of a broader effort to limit China's access to the most advanced chip-making tools and technologies. But the challenge goes far beyond just hardware. Producing 2-nanometer chips requires a highly sophisticated ecosystem, one that includes not only specialized machinery, but also rare semiconductor materials, advanced design software, and deep technical expertise. Much of this ecosystem is dominated by companies and research institutions in the U.S., Japan, and Europe, making it extremely difficult for China to source what it needs independently. Replicating this intricate supply chain within China's borders is a monumental task that could take many years, if not decades. Building up the necessary infrastructure, training talent, and developing homegrown alternatives is a slow and expensive process. Even with deep ultraviolet or DUV lithography as a workaround, the results fall short. DUV machines are less precise, and using them for advanced nodes leads to significant technical hurdles. Yields, the percentage of usable chips per wafer, would be too low for commercial viability, driving up costs and making mass production nearly impossible. Constructing a state-of-the-art semiconductor fabrication plant, or fab, now costs more than $20 billion, and that's just the beginning. The ongoing expenses for maintenance, upgrades, and skilled labor add up quickly. Developing a new process node, especially at the 2-nanometer level, demands even more in research and development, requiring years of trial, error, and innovation. China is pouring billions into this effort, but it faces a daunting competitor in TSMC, which has a decades-long head start, a proven business model, and a global network of partners and customers. The financial and technical gaps between China and the world's leading chip makers are enormous, and closing them will require not just money, but time, talent, and international cooperation. For now, these towering barriers keep China from catching up at the leading edge of semiconductor technology, and the path forward remains steep and uncertain. The 2-nanometer race is at the heart of U.S. China rivalry, representing not just a technological milestone, but a symbol of national ambition and global influence. The ability to produce the world's smallest, fastest chips is now seen as a key measure of economic and strategic power. With Washington determined to maintain its technological edge, the U.S. government has enacted sweeping policies to protect its semiconductor industry, viewing leadership in chip technology as essential for both economic prosperity and military strength. Export controls have created a great chip divide, restricting the flow of advanced technology and equipment to rival nations and redrawing the boundaries of global collaboration. This divide is splitting the world into two tech spheres, one led by the U.S. and its allies, the other by China and its partners, each racing to secure their own supply chains and technological independence. In one sphere, countries and companies enjoy full access to the most advanced tools, research, and global talent, pushing the boundaries of what's possible in computing and artificial intelligence. In the other, nations are forced to innovate independently, developing homegrown solutions and alternative technologies, often under immense pressure and resource constraints. Countries and companies must now choose sides, navigating a complex web of alliances, regulations, and shifting loyalties as they decide where to invest, source, and collaborate. The result is a fragmenting of the once global supply chain, with disruptions and shortages rippling across industries from smartphones to cars, and uncertainty becoming the new normal. Taiwan's dominance in advanced chip manufacturing makes it a strategic flashpoint. Its foundries are the beating heart of the global electronics ecosystem. And, Any disruption here could have far-reaching consequences. A single crisis could cripple the global electronics industry, halting production and innovation worldwide. In response, the U.S., EU, Japan, and South Korea are pouring billions into domestic chipmaking, launching ambitious initiatives to build new fabs, train talent, and secure their own technological futures. For these nations, semiconductor self-sufficiency is now seen as a matter of national security, vital for defense, economic stability, and global influence. This global subsidy race is reshaping the industry, driving unprecedented investment, but also raising the stakes for competition and conflict. While it accelerates innovation and technological breakthroughs, it also increases geopolitical risk, as nations vie for dominance and control over critical supply chains. The chip war is fueling both remarkable progress and rising tension, with every breakthrough shadowed by the threat of escalation. As the world stands at this crossroads, the future of technology and the balance of global power hangs in the balance, shaped by the chips at the center of it all. 2-nanometer chips will transform everyday life. Think faster phones, longer battery life, and smarter devices. AI models will become more powerful and accessible, driving breakthroughs in medicine, climate science, and beyond. The global AI market is set to explode, powered by these chips. But heavy reliance on Taiwan means any instability could disrupt supply chains, causing shortages and price hikes worldwide. The U.S. China chip war could also split the tech world, making devices and software less compatible across regions. Who controls 2-nanometer production will shape technology, economics, and society. For consumers, this race determines the cost, availability, and capability of tomorrow's devices. Experts agree, China's 2-nanometer ambitions face daunting hurdles. The lack of EUV access is the main barrier. DUV workarounds are risky and costly. TSMC's lead is built on decades of collaboration, investment, and expertise, an ecosystem China is only beginning to build. Progress at mature nodes is impressive, but the leap to 2 nanometers is another magnitude entirely. Most predict China will focus on catching up at less advanced nodes before tackling 2 nanometers. For now, Taiwan holds the crown, and bold claims of imminent Chinese breakthroughs should be met with skepticism. The story of 2-nanometer chips is one of relentless, painstaking progress, not sudden leaps. The outcome will shape the future of technology, economics, and global power.